Okay, so this one's know if it's in equilibrium. Well, there's two conditions for equilibrium. One is that the net force is zero, and the second is the net torque is zero. So the thing with the net torque being zero is that is not dependent upon where the pivot point is. So pivot point anywhere for that. So the net force, that's pretty simple to look to see if the net force is zero. The net torque is zero. You have to look at everywhere for a pivot point. So you have to choose a pivot point here to see if it's zero, pivot point here to see it's zero, pivot point here to see it's zero, and everywhere in between actually. But since that's where the force is applied, that's kind of where you want to check. Okay, for the next one here, we want to find the torque generated about 0.0 from this force. So torque is equal to force times the lever arm length times the sine of theta. So R would be the distance from here to here. And then this would be the angle here. So from here to here is R. This is the angle theta. And so if you want to know what R sine of theta is, because it's not telling us the angle here, realize R sine of theta is just simply the shortest distance between the pivot point and the line of action that contains the force. So here's the force that's like this. A line of action containing the force goes like this. And so I want the shortest distance between this point and this line. Well, that would be this distance here. So in other words, this R sine of theta is just simply 1. So it's going to be the force times 1. All right, so next one, we're trying to figure out what the scale reads here. So since it's balanced, we could pick a pivot point anywhere. Well, there's going to be a force downward here on the bar, force downward, and we know how much that is, 20 newtons. There's a force downward here, which is 10 newtons. But there's two upward forces. There's a force here, let's call it normal 1, and there's a force upward here, we'll call that normal scale. That's the one I want to know. So these two right here are unknowns. So I could write N1 plus Ns is equal to 30, but that doesn't help me. I need to use torque to figure this out. Well, you could put, just like back up here, you could put a pivot point wherever you want. Same thing here, you could put a pivot point wherever you want, but you should pick a point that is going to make it easier for you. And a point where it makes it easier would be right here, because then the torque this one creates would be 0. So let's put a pivot point here. And in that case, this force here tends to make this bar, so imagine this bar here. This force down here tries to make it pivot like this, and so that's pivoting counterclockwise. This is also trying to make it pivot that way. So again, that force there is trying to make it pivot up. So that's counterclockwise. And this force here is trying to make it pivot clockwise. So this one, which is 10 newtons, tries to make it pivot clockwise. And this one here, which is 20 newtons, tries to make it pivot counterclockwise, and so does this one. So in other words, the torque from the 20 plus the torque from Ns has to be equal to the torque from the 10, because those are both counterclockwise and that one's clockwise. Don't forget that torque is force times distance times the sine of the angle. Well, the angle for every one of these is going to be 90 degrees. So it's going to be 20 times 0.1, because each one of these is 10 centimeters. So 20 times 0.1 plus Ns times 0.2 equals 10 times 1, 2, 3, 4, 0.4. And solve it. All right, the next one. Let's see. We're trying to find the tension in this wire. So what I'm looking at is I'm looking at this rod, and there's a whole bunch of different forces on it. First of all, there's a force right here. We'll call that the weight of the sign. The beam itself has weight, and that acts right in the middle of this. So the whole thing's 1.70, so half of that. So I think that would be 0.85. Okay, so we know what that one is. There is a force from the tension, which is the one we're trying to find. Tension. There would also be a force, because tension is kind of pulling it to the left a little bit, so there must be a force right here outward. Kind of, I'll call that normal in the x direction. There might also be a force this direction on that pin. I'll call that normal in the y direction. Maybe it's not really upward, maybe it's downward. I don't really know. But those are all the possible forces. And just to be clear, I only know the weight of the beam, I know the weight of the sign, and I know some distances and I know some angles, but I don't know that force, or that force. And I only care about the tension. So I probably want to put it, I can't really solve this using the first condition equilibrium. In other words, Ty plus Ny equals this weight and that weight. That doesn't really help me because that's two unknowns. Neither does it help me to say that Nx equals Tx because those are both unknowns. So I probably want to use torque, and I want to put a pivot point that will get rid of as many unknowns as possible that I don't care about. So I think I'm going to put it right here. That way the torque that each one of those would cause would be 0, because given that torque is force times distance times the sine of the angle, the distance is 0 from the pivot point. Okay, so this tension force tries to pull it upward, so that would be spinning around counterclockwise. And those two weight forces try to pivot it downward, so that would be clockwise. So it's going to be the torque from the tension is going to be equal to the torque from the beam plus the torque from the sign. So the torque from the tension would be the tension times the distance away, which they say is 1.35, times the sine of 35, because remember torque is force, distance, sine of the angle. And that's going to be equal to the weight of the beam, which is 1.55, times half the length of this, which I think is 0.85, times the sine of 90, plus the weight of the sign itself, which is 215, times the distance away, which is 1.7, times the sine of 90, and then solve it for the tension. Okay. On the back side. So let's see here. We're going to kick this hover puck. It's turned on, and we're going to kick this off center at different locations. B is right on center. Okay. Determine the net force and net torque on the hover puck. Well, we know what the force is, and there's no friction or anything, so it's pretty easy to find the net force. Each one of these locations is just simply that 5 newtons. To find the net torque, it's going to be the force times the distance times the sine of the angle. So at A, that would be 5 times, well, it's 0.05 meters away, so 5 times the distance of 0.05 times, well, that would be perpendicular to the radius, so that's sine of 90. So 5 times 0.05 times sine of 90. At B, the torque would be 0 because it goes right through the center, so R would be 0. At C, it's going to be 5 times, let's see, that would be half of that, which would be 0.1 times the sine of 90. Okay, number 6. Okay, calculate the reaction forces A and B. All right. So there's a little gap on the ends for expansion during wintertime, so there's no touching there, but there is a force here that's up, and a force here that's up. I don't know how big they are, so I'll just call this force A, force B. And it looks like there's three other forces: weight force of the car, weight force of the bridge itself, weight force of the truck, SUV. All right, so I'm trying to find those two forces. So I could say FA plus FB equals the sum of those three. Well, that's not helpful because there's two unknowns, okay? So I probably want to use this idea of torque. I want to put a pivot point somewhere where there's an unknown to get rid of one. So let's say we put a pivot point here, okay? So this car right here is going to try to spin it this direction, which would be counterclockwise. These two forces, these two weight forces, try to spin it clockwise. And then FB is also trying to spin the bridge counterclockwise. So it's going to be, I'm going to call this car and this here truck. So it's going to be the torque from the car plus the torque from FB, because if you remember those are trying to go counterclockwise, has to be equal to the torque from the bridge, which is that 20,000. So bridge plus the torque from the truck. Okay, so the car, it would be 8,000 times the distance away, which it looks like it's 15 times the sine of 90. For this one, it would be force B, which we don't know, times the distance away, and you'd have to add up all of those distances to figure out the distance away from the pivot point, times the sine of 90, equals 20,000 times the distance away, which I think is 35, times the sine of 90, plus 8,000 times the distance away, so you have to add those two together, times the sine of 90, and then solve for FB. Once you know FB, then you can go back to your one equation where we have FA plus FB equals those three forces added together and solve for FA. Okay, last one, number 7. Okay, so we're trying to figure out the reactionary forces at A, B, C, and D. Okay, so it says that these planks are massless. We're saying they're essentially massless. So first, let's start up here. There's going to be a weight of the person downward. And there's going to be two reaction forces, FD and FB. Both of those are unknowns. We don't know those. So we could say FB plus FD equals the weight, but that's not helpful because there's two unknowns. So we'd have to put a pivot point somewhere to get rid of one of the unknowns. How about right here? And so we could say the torque from the weight, which is trying to spin it this direction clockwise, it must be equal to torque from FD. Torque from the weight has to be equal to torque from FD. So we know what the weight is, it's 480. So it's going to be 480 times the distance away, which is 9, times the sine of 90, equals FD times the distance away, which is 12, times the sine of 90, solve for FD. Once you know FD, then FB plus FD equals the weight, so you could solve for FB. Then, to figure out A and B reaction forces, so I'm going to erase this now. So now I'm looking at the bottom one. So there's going to be a force from B downward. It's the same magnitude as what you just found. I'm going to call it FB again. Same magnitude because it's balanced. And there's going to be two reactionary forces, FC, which we don't know, and FA, which we don't know. And we're going to do the exact same process again. We just found FB from the first part of this, and now you can find FA and FC. That's how you do it.